Hey guys, welcome back to AlgoYogi. We are doing linked list series and our next problem is sort list. All right, let's go to the problem on LeetCode. So given the head of a singly linked list, return the list after sorting it in ascending order. And in the constraints, they have basically given us the nodes. Yes, okay, so first thing first, I think the best solution, the brute force solution that you can come up with, turn this into an array, sort the array using a merge sort or quick sort or whatsoever. And since initially as a brute force approach, you could just simply use bubble sort, easy to implement, basically n square time complexity, taking one element, sorting it, placing it, the largest element in the end, remaining list resort, you keep taking one biggest element, bubbling up to the top, the biggest elements. That's why it's called bubble sort. But now that's not what we are doing right now. We will directly start working with this follow-up, that is, can you sort the linked list? So if you want to use merge sort, go to the array hash section, and we have already basically solved in here this particular problem, sorting the array, so that you can definitely follow up and then just do it that way. We are going to do it in the linked list way without converting it to an array, but definitely go for that approach because that's like the most intuitive, easy to come up with, best, and really easy to implement. Now what we're gonna do is we're gonna do merge sort. But do it on a linked list, right? Rather than doing it on an array, we're just gonna do it on linked list. So there are like a couple of things, how we're gonna find the middle node, and if we are finding the middle node, and how we actually merging these two sorted list. All right, that's what merge sort is about. So merge sort is not the important topic here, but what's most important is like merge sort on linked list. If you want to see the merge sort, then go to the array section and look it up on algoyogi.io. The solution would be there, so you can watch that first and then try to do this. Let's get into it. Let me change the view here. So in merge sort, what we do is we have this list over here. And let me show it on oh good, okay, let me have 4, 2, 1 and 3. On an array, what really happens is you basically split it into 2, and then you keep splitting them until you basically are with one element. Since it's just one element, it's already sorted. So what do? You take these two, you merge them, and you merge them in a way, you're merging them into a sorted list. Basically, these two lists are sorted and you're merging them. Merging two sorted list is big of n time complexity. Okay, so breaking this entire thing down until you reach one node with one value, it took us log n time complexity. You're basically dividing it into two halves. So if you have some value and you just wanna, at every level, you just like binary tree, you're just bringing it, basically dividing it to half at each level. Then it will take you log n time to basically reach to the leaf node where you end up with one value. Then merging two sorted lists together takes n big of n time complexity. So together this solution would be n log n time complexity. Okay, and remember these two sorted lists, merging these two sorted lists would be basically big of n So after merging them, this is what we get. And here as well, these are already merged. You know, when they were merged, they were already sorted. So now we get just this, and then we're gonna basically merge these two, and then we get basically 1, 2, 3, and 4. Okay, I'm not gonna just remove it. So this is what you return back. Doing it with the linked list nodes is definitely a little tricky, but it's only tricky in a way that our finding the middle node and merging two sorted lists, that's the only tricky part. But remember, we have done a problem. I think that was an easy problem where we merged two sorted linked lists. So we will do the same thing. And for finding the middle node, we will use this approach that we have done earlier using slow and fast pointer. So once fast pointer reaches the end, then your slow is in the middle. So then that's what you can return as middle node, and that's where you do this split. And using pointers, we know how we're going to actually split. So let's basically do that. So we'll have three functions. First is basically sort list we have. So first thing first, let's do this. We're gonna have check for the edge cases. If head is none or head dot next is none, and that means that we have either no node or one node. That means we can just return that node. If it is none, then return none. If it is one node, then you return that node, and that's a sorted node already. One node is sorted, all right? And this is a base case for us when we are actually calling this self dot sort list function onto split list from the middle. All right, so let's try to split it into two lists. All right, so what I'm gonna do now is have my left pointing to the head, and then I'm gonna point my right to basically I'll have self dot mid get mid. I'm gonna call it get mid, and I'm gonna send in to get the mid. I'm gonna send in my left pointer. I cannot send head over here. Remember, I'm gonna send, or I think I can send head over here as well, but they're both pointing to the same node, and they will point us to the same node even if they were splitted. But now once we get this, now I have this right, let me call it mid, or should I call it right? I'll just call it right. Okay, if I'm trying to get the middle, then what I do is I get this middle node and I want to set its next to, so this is not going to be the right node. I'm going to call it temporary node, and this temporary node is going to store the middle node, and right would be my right would be basically temp. Okay, my right is pointing to temp, and my what I want to do is I want to point this temp dot next to none. Okay, so this is what's happening. I have this temp in the middle. I can call it middle also, but I have this mid node, and I am pointing my right to mid. So I have that as a stored pointer to mid node, but then I want to remove this mid dot next. Right would be mid dot next. Now it makes sense. And mid dot next, and now mid dot next is set to none. All right, tricky to comment, but we have done it. We nailed it. Okay, so we have this left and right pointers pointing to left linked list, right linked list. What I want to do is sort them. So I'll call it basically sorted left, and that we will do is basically from this function self dot sort list. So sort list, then we are just basically providing what do we want to send in. We want to send in left, right? So I'm just calling it left, and then I want to send in right, sorted right. Do I need to actually, what this will return is these two. Yeah, I mean, it's an okay way of calling them. Okay, sort list, and then you're sending the right pointer. All right, so we're sorting left half, we're sorting right half, just like our main function is sorting us. Okay, so it's a recursive function, so we can definitely do that. Now we have this sorted left and sorted right. Now what we want to do is merge them together. So self dot merge and sorted left and sorted right. So these two, and then finally we just return this. Okay, so I can, rather than this, I could just call this in the end. That's it. Now let's write down our helper function. All right, what is our first helper function? That is get mid. So get mid, and get mid will basically take, I'm gonna call it head. Then I'll have my current pointer. So getting mid is basically, you want to have two, slow and fast pointer, as we talked about. Slow and fast. Slow pointing to basically head, and then fast pointing to, like, just move it one forward, and that's where we started. Head dot next. Then we want to have a while loop, while fast and fast dot next, because that will reach the end of the list first, and then we move slow dot next, and then fast dot next fast dot next. All right, then once we have that, we can simply return slow. That's where it will be pointing to exact middle node. All right, now this is done. Let's write our second helper function, which is merge. Merge will take we can say I'm gonna call it L1 and L2, two sorted list, and we have written this function quite a few times, and that you can check it out in, I think it's somewhere here, you will find it, merge two sorted lists. So this is exactly what we are going to write here, but since it's a new problem, I want to write it from scratch, and rather than copying it from our previous solution. Although if you want we could, but let's code it up, because we are here to practice our coding skills and not like copying skills. Okay, so dummy node, let's create a dummy node. Let's call it pointing to 0, and it's then our current pointer pointing to dummy, while L1 and L2. So if both are there, since if both of them exist, then if L1 and L2, that means one of them, if they're not equal length, or I think one of them might end up, if they don't have like equal number of greater and smaller nodes, the nodes are equally distributed. I don't know how to say it, but I think you understand what I mean to say. So what can happen is if L1 dot val is smaller than or equal to L2 dot val, then what I want to do is my current dot next pointer will be list node with L1 dot val. This is what I'm going to use, and I will move my L1 to L1 dot next, and I will move my cur to cur dot next. Okay, otherwise I'll do the same thing, but remember we will do it for L2. Okay, so otherwise L2, that means L2 value was smaller. It's a merge. We are merging two sorted list, so L2 dot next, cur dot next. Okay, that's it. But then sometimes what might happen is one of the list is fully used or maybe half used, and the other one is remaining, something like that. Then we will check if L1, then my cur dot next will be L1, and if L2, and either of them will happen. Okay, cur dot next would be L2, and then finally we just return dummy dot next. You can't return cur. Okay, don't return cur, because current is in the end of the list, the sorted merged list, merged sorted list, or sorted merged list. You return dummy dot next. All right, then that's it. I am very, very hopeful that this will pass the test, unless there is a little bit of problem. Simple fix, because it's the Python thing. Since it's a class level method, then we have to provide this self keyword here. Okay, I think that's it. Yeah, okay, let's run it. That was just stupid. Okay, yes. All right, let's submit it. Very not super efficient, but we fulfilled the criteria here that we have to do it in n log n time complexity and big of 1 space complexity. Let's write down. So time complexity, we talked about splitting an array or linked list till the end. When you reaches to every leaf node becomes just one value, then just one node, it will take big of log n, and merging sorted to list is big of n, so it's gonna be big of n log n. All right, and then space complexity is what made this problem really tricky, and that would be big of 1. We didn't use any extra space, unless you're talking about the tech stack, like not tech stack, the stack, the recursion stack, and we considered that basically log n. Okay, anyway, or that was for the time, but like, yeah, for space also you're storing it onto the stack. That's implicit. Let's mark this solved and see you guys in the next problem. Until then, bye bye. My brain is fried.